Down the game action. The bees, mosquitoes, and dragonflies are bombers. Any one of these insects will...
What you just saw were humans playing the popular Atari game Centipede. What you are seeing now is a novel reinforcement learning algorithm called DreamerV2 dreaming about that same game. But before we dive into how it all works, we first have to talk about why the algorithm is playing Centipede of all games, introduce the authors of this paper, and refresh our knowledge on reinforcement learning a little bit. Why is it playing Atari games? The agent DreamerV2 from the paper that we are going to talk about was mostly evaluated on an ATARI benchmark. It is composed of 55 games that are challenging for both human players and reinforcement learning agents alike. They require different skills like quick reaction times, pathfinding, predicting enemy behavior, long-term planning, exploration, and some have really sparse rewards, what is actually really challenging for reinforcement learning. And because of their popularity, there exists strong human records to compare against, like the world record we just saw in the intro. Almost all reinforcement learning algorithms nowadays are evaluated with this benchmark, so they can be compared to each other easily. The paper Mastering Atari with Discrete World Models that we are going to talk about was published at the ICRL, which is the International Conference on Learning Representations. It's one of the 3 major machine learning and artificial intelligence conferences. Now to the 4 authors of this paper. Danijar Hafner is a PhD candidate at the University of Toronto. He is also a visiting student at the University of California, Berkeley. At the moment he is an intern at DeepMind, but at the time of writing this paper he was an intern at Google Brain and was interning there for 6 years. The second author, Timothy Lillicrap, is senior research scientist at Google DeepMind. He is also adjunct professor at the University College London, and he worked on AlphaGo and AlphaZero in the past. Mohammad Nuzuri is staff research scientist at Google Brain. He made his PhD in computer science also at the University of Toronto. And the last author is Jimmy Barr. He is assistant professor at the University of Toronto and also made his PhD in computer science there. And he's famous for that he worked on the Adam optimizer, which is the default optimizer for TensorFlow at the moment. Now let's talk a little bit about reinforcement learning. In reinforcement learning, you try to program an agent that can learn by itself to interact with an environment. Its objective is to maximize a reward signal from the environment and do so only by his own experience. He can interact with the environment by receiving the current state of the environment as, then choosing an action, that's his output, then sending the action into the environment, then the environment processes the action and delivers the next state to the agent together with a reward signal. This loop is repeated many times, and so the agent can learn from the reward signal and get better and better and choose better actions for each state. There are many techniques how to program such an agent. One of them is Actor-Critic learning, and because it is used in the DreamerV2 agent that we will talk about, we look at that. In Actor-Critic learning, we open the black box of the agent, and what we find inside are 2 other black boxes. One of them is called Pi, the policy of the agent. Policy is a function, usually a neural network, that takes the current state of an environment as input and outputs a probability distribution over all available actions. From this probability distribution, you can then sample an action, and this action is what the agent will output and then execute in the environment. To train this policy, we could use the rewards that we get from the environment directly. That would result in a so-called policy optimization algorithm. But for Actor-Critic learning, we also use a different kind of reinforcement learning algorithm at the same time and use that to improve the policy, and that's the so-called value function. The value function also gets the state of the environment and outputs a value, which is just a scalar value like the number 10. This value contains the information of how good the current state is. Now, if we wire everything up to actually learn from the reward signal, it would look a little bit like this. The top part is just the reinforcement learning loop I already described. Now, we also feed the same state into the value function and get the value for the current state. We then use this value to improve our probability distribution. To train the value function, I just drew a green arrow, which is a huge simplification of what's actually happening. But you can imagine that we use the output of the value function, like the value of the state S, and compare it to what we predict for the state as t+1, which we get in the next time step, and then see if that matches the reward we actually got from the environment. Now, if we trained the value function, we then use the value of the state to stabilize the policy updates. Again, this drawing is a huge simplification of the actual algorithm, but that would be a little bit out of scope for today. Now back to that image. Instead of learning a good agent, it is also a possibility that's quite interesting to learn a representation for the environment. Here you can see M, the model, is what we want to have, a representation of the environment which has the exactly same in and outputs, and ideally it could exactly replace it. Why would we learn such a model? There are actually many benefits. One of them is we could learn a little bit stable. We could learn more stable from more data, because learning policies directly from raw pixels, like we have to do in Atari, can be unstable because in the images there's noise, there are textures, there are blinking lights to keep the player entertained, which are not actually important signals for the agent. By learning the environment, we could learn the dynamics model of the environment, like what is actually happening, what are the physics, what is moving, and could compact the representation. And one big benefit is if we don't have access to the environment, or if the environment is really slow, we can learn a much faster model of the environment and can train against the model instead of the real environment to improve speed and efficiency. How would that look like? We would pretty much feed the model the same information that we feed the real environment, and then just take the difference of what the environment outputs, that's the state one step in the future, and the reward, compare the both and use this as a gradient to improve the model. Now that we all are up to date in terms of reinforcement learning, we can take a look at DreamerV2, the star of the show and the main contribution of this paper. DreamerV2 is a model-based reinforcement learning algorithm. That means it trains a world model of the environment and at the same time trains an agent. The special thing about is that the agent is actually only trained on the learned model. So the agent never sees the real images from the real Atari game, but just the learned representations. Even though this might sound a little bit limiting, it outperforms current state-of-the-art single GPU reinforcement learning algorithms. What you can see here flickering and what you saw in the intro are actually the dreams of this world model. If we zoom in, you can see Pac-Man. For some reason, Pac-Man is a blue human in this environment due to copyright. But in the top row, you see the actual Atari emulator. The middle row is what the agent dreams. And dreaming in this case means that he only ever sees the first frame of the top video, and all following frames that you see in the bottom are what the agent imagines that will happen. It's completely predicted 50 frames into the future. And as you can see, if I didn't tell you which one is which, I don't think you can tell them apart. The bottom row is the difference between the top and the bottom picture. You can see in blue if something is missing in the prediction, and in yellow if something is there that it shouldn't be. Also, this is the example from the intro where the agent is playing Centipede. Just remember, the middle row only sees the first frame of the sequence and then imagines the whole rest. This includes all the enemy movements and physics interactions and shooting of bullets and killing of enemies, and even the counter. Dreaming isn't the only thing the algorithm can do. On the right here you see in these 6 animated images you see how the trained agent actually plays. These are videos of the evaluation episodes that the agents played that contributed to the final score evaluation that we see in a bit. And here you can see it is actually pretty good in some of these games. Also in the bottom there are 2 examples where you can see that the algorithm not only works on 2D Atari games but also can work for continuous control in 3D environments. Now we take a peek under the hood of this algorithm. As we recall, we try to learn a world model. That means we try to learn a set of neural networks that represent the environment with all its inputs and outputs exactly. The first step of DreamerV2 is an autoencoder. Autoencoder means that we have convolutional neural networks that compress the input to a very small state. In this case, it's 32 by 32 categorical vectors. And this small amount of data has to represent the whole game. It has to be able to be reconstructed by the red structure on the right to produce the input image again. And this actually works. But the authors didn't stop there because an autoencoder is not that special. The first thing they added are gated recurrent units in this purple network. That means the network has a memory that it can keep from time step to remember things about the last time step. This hidden state that you can imagine like the memory of the agent is called H here. You can see on the left side of the purple network it's H from the previous time step that's coming from the left, but it's actually identical to what the network outputs to the right, but just one time step earlier. The state gets first compressed with the autoencoder. Then another small network combines the compressed state with the memory of the agent and outputs these 32 categorical variables that I told you just a moment ago. These categoricals are then concatenated with the memory, so the memory is just appended to them, so the decoder network can use both the categoricals and its memory to reconstruct the image. This would already be enough to train the autoencoder, but to model the environment correctly, we need to go one step further. We need to not predict the same state, but we need to predict one step into the future. And that's what this turquoise neural network is for. It only gets its own memory as input, so it doesn't see the actual image at all and tries to predict the 32 by 32 categorical vector directly. Also, the model needs to output the reward, so we just add that to the end. We use the combined memory and compressed state and send them through a small neural network that predicts the reward. To close the training loop and to actually train this, we need an agent. The agent is not trained in this step, so we can just handle him as a black box for now. To wire everything up, you now see a lot of arrows, but don't be scared. The easy one is on the right. The reward is just compared to the real reward we get and is backpropagated just through the reward stage of the network. Authors also backpropagated it through the whole network, but they experimented and found out that is actually indifferent what they do, and like this it's a little bit easier, also easier to draw. Now, one of the interesting things is what happens in the middle. You see this blue line, we compare CT and C roof T, which is like the actual compressed state of the network and the predicted next state of the network. And we can see if they are any different, if the network predicted correctly the next state of the environment and propagate this loss back through its look in the future network and through its memory network. On the other hand, we can train the autoencoder chain at the bottom. We can compare the decoded image that comes out with the image that came in from the environment and calculate a difference and a loss there, and then backpropagate that loss through the whole chain, like first through the decoder, then through the categorical encoder that encodes the memory together with the compressed state, then through the encoder of the main network, and also further back through the memory network. Now there is something special. You see the memory network gets a loss signal from 2 points actually, from the autoencoder and from the difference of the categorical states. And this is actually a little bit of a problem because these two objectives play like tug of war with each other, and they can lead to a resonating effect that the network doesn't learn a good representation. The researchers noticed this, and they weighted the loss of the categoricals with 1/10 of the other loss, so that the network first learns a good autoencoder with good categoricals and then tries to predict the categoricals correctly. Otherwise, it could learn not so good categoricals, but learn to mimic these bad categoricals very good. Like if they are only a simple pattern, like only once in the first row and nothing else, it can learn very precisely to mimic this pattern, but it's not at all a good representation for the actual game. Now that we trained the model, we can use the model to train the agent. This will look a little bit something like this. First, we feed one real image into the encoder through the chain to get the first categorical representation. Then we send this to the agent. The first difference you see now is that the agent actually gets the categorical representation and no longer the whole image. So it only learns from these categoricals. But he gets this real categorical as first input. He chooses an action, and this action is then not evaluated in the real environment, but already in our mock environment. It goes through the memory stage, which takes an action and a categorical. This would be also the first categorical that we calculated down here, and also its own memory, which would be randomly initialized in the first step, and then calculates a new memory, sends this new memory to our predictor network, which computes one step into the future, the prediction of the next state CT. This will be concatenated with its memory to be sent to the reward predictor, and then our predicted categorical and our predicted reward are sent to the agent as if they came from the real environment, and we can train this loop here on top for some steps into the future. If we train too many steps into the future, the difference between the real environment and the simulated environment will get a little bit too large, but in the paper they trained for like 15 steps into the future each time. So we have a data efficiency of 1 to 15. We need only one real experience for every 15 simulated experiences, which especially for complicated environments can be a huge benefit. The training of the Actor-Critic agent and the environment take turns, because a better agent may be able to find new states in an environment that the learned environment has never seen before, and vice versa. We need to improve the world model and then train the agent again on the improved world model so it can learn new behaviors. Now that we know how it works, let's see how good it works. These are the final results from the paper. On the top left, you can see it not only matched the performance of the top single GPU agents, it beat them actually by quite a large margin, which is amazing because model-based learning environments haven't been around, and to not only catch up, but to beat existing algorithms is quite amazing. On the top right, you can see the performance graphs. These are averaged over all 50 Atari games that are evaluated. On the left, these two are compared to a gamer mean. That means 1.0 is the average score of a human gamer. The authors of this paper actually criticized this metric and proposed the metric to the right, which compares to the currently standing human world records. They also advocate clipping the record so that superhuman performance in one single game, where the agent is much better than a human, doesn't explode the score like you see in the third image, but it just gets clipped to 100%. Like we reached the world record, it only counts as 100%. This is actually quite promising, because that means that on average over all 55 Atari games, DreamerV2 only achieves a quarter of what the human world record holders are able to achieve, so we still got some air to breathe left before robots conquer us. Also here you can see an overview of actual learning curves of some of the Atari games, that you can get a feeling how much the agent improves over its predecessors. Blue is the graph of DreamerV2, orange is the graph of IQN, and green is the graph of Rainbow Deep Q Learning. Now, to conclude this presentation, we can do something that's quite rare for a new research paper. We can take a look at the follow-up paper, which is already released, although DreamerV2 is only a year old. Dreamer version 3 uses the same architecture as DreamerV2, only has a few iterative improvements, uses a little bit different networks and network structures, but is the exact same algorithm that I just described, was a little bit more fine-tuned and hyperparameter optimized, and now is the first algorithm ever that beat the Minecraft Diamond Challenge, which together a diamond in Minecraft without any human knowledge, just by playing. Also, they evaluated DreamerV2 and DreamerV3 on much more environments, and you can see DreamerV3 is actually quite performant on multiple tasks, not only Atari. But that was it for my presentation. Thank you for listening, and I'll be happy to see you at the questioning.